All right, so we did calorimetry a little while back, but now we have to go into things that are using the balanced equations a little bit more besides that stoichiometry aspect that I did. My first slide is just a reminder of what you just did. Again, with bond energy, it's the amount of input versus output. Now, you wrote an equation down on your reading guide. That equation is not given to you. And as you're going to see when we dive deeper into thermodynamics during the course of not only this unit, but our last unit of this semester, that equation can be forgotten or mixed up very easily. So remember, what you're doing is you're breaking reactant bonds. And one of the issues that students have, and maybe even later on today, and especially after next class period, so that's why I'm saving the last calculation for next class, because we probably could squeeze that in today. I just put too many things at once; they start jumbling together a little too much. We got to keep track of what way to do our calculation and when. And part of that's based upon what you're given. And if you see anything resembling Lewis dot structures or bond energies of a C double bond O is this value, things like that, that's got to tell you that you're using this bond energy example. So I was going to go over this problem with you just to give you one example as well that I would do of a decomposition of hydrogen peroxide, because this is a fairly common reaction that can have a lot of extending questions as well. Because again, I'm always thinking about, I see a problem in this unit, how could other topics relate to this? We actually used to do a kinetics lab with the decomposition of hydrogen peroxide. I mean, heck, this reaction is weird because it's a redox reaction where the oxygen in the peroxide is both oxidized, because this is a -1, and it would go to a -2, or I'm sorry, to a 0, and it's reduced to -1 to a -2. I mean, it's an unusual reaction. Again, remember, Lewis structures are needed in order to do this as well. Now, your method of organization is up to you, but typically what I do, especially if it's a larger problem, is I try to identify how many of each type of bond there is. So that's all my reactants. In order to break my reactants apart, I have to break 4 of the HO bonds. 1, 2, times 2, because of 2 coefficients. I have to break 2 of the OO single bonds. So it's reactants minus products. And in the products, then, I have 4 of the HO, 1 of the O double bond O. Which, boy, before even plugging in numbers, you can kind of see that the 4 HOs on both sides would cancel each other up. So really, all you're doing is subtracting 2 of the OO single bonds versus 1 of the OO double bond. Now, if I were to plug in the values, and again, this is something that would be given to you, it would be 4 times 464 plus 2 times 142. And you subtract from that 4 times the 464. Again, different text will give you different values. Now, 460 is a very common value for that otherwise. 498, 499. Again, this is 2140 minus 2354. Decomposition of hydrogen peroxide is exothermic because it's -214 kilojoules per mole. So that would be a bond energy problem. Again, at the end of the reading guide, it started talking about weaker bonds being longer bonds, stronger bonds being shorter, things of that nature as well. But hopefully review from Chem 1. Because my last slide, because I only have one other slide, is the new thing that we have to learn today as well, that we haven't seen in Chem 1 before. I used to do a whole packet to lead students into this new calculation, but I'm going to try it a little bit different this year, where I'm just going to give you a slide of notes, and then hopefully with you doing practice problems, you'll be able to figure this out. So, heat of formation is the next thing that we have to go over. This reaction, or this equation rather, that I have in bold, is an equation that is given to you on your equation sheet. The heat of formation of the products minus the heat of formation of the reactants. The reason why I introduced this today to you is we, in essence, with bond energy, if it's a synthesis reaction, could figure out the heat of formation for anything. Take the reactant bonds minus the product bonds, figure out how much energy is to make that happen. Quite frankly, if we had a decomposition reaction for hydrogen peroxide, I could just flip it around, because the reverse reaction then should give me the opposite values, and I could solve for the heat of formation of that. But the heat of formation, that's your delta HF. These are things that will be given to you. These are values that represent, hey, here is what that value is for this thing. Now, don't know if you pick up on the fact that there's a degree sign in this as well. If you see a degree sign for pretty much anything in chemistry, that means that the scale that they use is man-made. For example, degrees Celsius, degrees Fahrenheit, Kelvin. Not a degrees Kelvin, Kelvin. Because Kelvin has a zero number that is not made up by man. Degrees Celsius has a zero number made up by man. Degrees Fahrenheit does. Heat of formation does as well. Basically, when you're going to be looking at Appendix 2, so the back of your book you're going to have to use a little bit today, what you're going to see is that some things are given a zero value. That's considered their most stable state. So for example, I know oxygen gas, O2 gas, is considered normal and stable. So they just gave that value as zero. And then they compare that versus other forms of the oxygen. Maybe it's ozone, O3. Maybe it's O2 as a liquid instead, because that's not as common and stable at our normal conditions. So then the numbers for the heat of formation are based upon that. So first off, don't be alarmed if you see a zero for some things when you look it up in the appendix, because when this was created, they just designated zero values, and then how close are you from this? How much do you veer from what we consider to be normal? Otherwise, this is practice in mathematics. But again, it requires a balanced equation. However, this does not require Lewis dot, because we are no longer figuring out bonds broken and bonds formed. Instead, we're taking the heat of formation of the products minus the heat of formation of the reactants, and that will give us our delta H, our enthalpy for that reaction. So, like the last thing, I want to give you one sample problem here. Actually, there's two different parts I'm going to give to you with this to kind of wrap up notes. So calculate the enthalpy of reaction between solid aluminum and iron 3 oxide. Now, again, how do I know which one to use? They would give you delta H of Al equals delta H of Fe2O3 equals. So they'll give you those numbers prior to solving. So it shouldn't be too tricky to determine which version you have to use. But remember, just before this, we did reactants minus products because that was bond energy. Now with heat of formation, it's products minus reactants. Now summation, and again, we have to take that into account as well. Two aluminum solid. Be careful when you look things up on your appendix that you have the correct phase notations for things. Everything's solid here except for the iron at the ends of liquid. Does anyone know this reaction? Iron thermite, I believe is what this is. You're making lava. So you could Google reactions with this. Heck, I think I saw an episode of Mythbusters once where they did this reaction on top of a car and just split it in half because it started making that lava. It's going to be exothermic. We're going to prove that right now. So what I would do is I would look up the values for these different things, but now if it's heat of formation, it's products minus reactants. So if I look up the Al2O3, that gave me a value of 1675.7. Again, everything here is kilojoules per mole. Plus 2 times the 12.40, which is for the liquid iron, minus 2 times 0. Solid aluminum is the most stable version, so that was given a 0 value. Plus a negative 824.2. And I often mathematically like to then figure out just the total value of the products and the reactants. If you are good enough just to solve it all together, that's fine. My two negative signs cancel each other out. It's not a tricky equation. Quite frankly, this products minus reactants you're going to see in April when we go over something called entropy, when we go over something called Gibbs free energy. It's going to keep on popping up of products minus reactants. When you look at your appendix 2 for these heat of formation values, again, it will give you different columns for different values. One being the delta H, one being the delta S, one being the delta G. So in thermodynamics, this products minus reactants is a very common thing to use. But the issue is, like I said before, every day I'm showing you a new way to do some of these calculations. You have to be familiar with all of them and know when to use which one. And today, since we reviewed what we went over in Chem 1, it is kind of the opposite. And that's where some people would flip the sign then, because they would flip these two parts. So you have to keep track of which one you're using and then use it properly. I have a little bit more to go over then on this last slide. Because I could give you an extension of this, which is kind of combining what we did with our first calculation of this unit with heat of formation. I could say you started off with 27.0 grams of aluminum, so tell me how much energy now is evolved in this reaction. Because if you remember at the beginning of this unit, I just gave you an equation, I gave you the delta H at the end, and you kind of did a little bit of stoichiometry in order to figure out what would then be the amount of energy given off. Well, now I can eliminate that step that I gave you day one of here's the reaction and its energy, because you could solve for the reaction's energy. That's what we just did. But then I could still make you do a little bit of stoichiometry with that. So if I go back to what I have here, here is my delta H of the reaction. If I started off, let's use a different color, with 27 grams, 27.0 grams of aluminum, again, convert to moles. That's our kind of golden rule here. Now, that would get me moles of aluminum. If you remember from what we have discussed before, there are 2 aluminums for every 1 reaction. So that's where a little bit of stoich comes in, because this value right here is per mole of reaction. So what I should do next is that there's 1 reaction for every 2 aluminums. That way, not only do my grams cancel out in step number 1, but my aluminum cancels out in step number 2. Now I'm in moles of reaction. Now I can use my delta H that I solved for in the previous step as the last conversion. It's negative 826.7 kilojoules per 1 mole of reaction. That would get me negative 413.4 kilojoules. So you could just do the top part that I had in black, where, hey, solve for the enthalpy for this reaction. Or we could take it a step further, where we give you an amount of either a reactant or a product. Because again, we could say 13 grams of iron was produced. How much energy was involved in this reaction? Or we give you an amount to start off with, like I did in this problem. Either way, we can combine now a little bit of today's stuff with day 1 material as well.